This video will focus on atomic nuclei, specifically the subatomic particles, and how we can use isotope and atomic nuclei notation to indicate the number of subatomic particles. So, quick review of the subatomic particles that we find in an atom. The nucleus is positively charged, and that's in the center here, and it contains two particles, a proton with a +1 charge and a neutron with no charge. Atoms are electrically neutral overall, meaning that there has to be another particle that has an opposite charge of a proton, and that is the electron, and these orbit the nucleus. Electrons have a -1 charge, which is equal and opposite to that of the proton. These particles have different masses, though. Proton and neutrons are very close in mass, and they're about 2,000 times heavier than the electrons, like 1,876 times or something. So they're about 2,000 times heavier than the electron. And so we say the relative mass would be 0.00055 for the electron to 1 for the proton and the neutron. And we actually call this 1 is a special unit, and that is the atomic mass unit. And so the atomic mass unit is just a shorthand way of saying the mass of the proton, and which is roughly also the mass of the neutron. So originally, when Dalton posited the first modern atomic theory, he thought that atoms of each element were identical, and that proved not to be true later. They discovered electrons, and then as scientists were discovering the nucleus, other scientists were looking at other cathode ray experiments and finding that they were getting a lot more what they thought to be unique elements in between uranium and lead. So uranium is a radioactive element, and they found that when they watched it decay over time, they would get more elements that between uranium and lead than should have been on the periodic table. And so what they actually found was that some of these elements had the same number of protons. And so that was how they realized that there was a different particle that had to be varying in the nucleus. And later, when they found neutrons, they discovered that it was actually the neutrons that varied between isotopes. So this is a picture showing the 3 isotopes of hydrogen. So we've got hydrogen or protium, but nobody really calls it that. Hydrogen 2, which is deuterium, and then hydrogen 3, which is tritium. And each of these have 1 proton because they are a hydrogen atom, but the number of neutrons is different in each one. And so these atoms of the same element have different numbers of neutrons. We call those isotopes. An isotope is from a Greek word that means same place, because they ended up in the same place on the periodic table. And this idea to call it that came from a friend of one of the scientists. She was a Scottish physician, and they were talking about their research, and he explained his research to her, and she suggested the name isotope. So to review the notation we use here, mass number is the number of protons and neutrons added together, and the atomic number is just protons. The mass number is here on top, and then the atomic number here. The Z comes from a German word that just means number, but that's what the A and the Z notation mean. And then X here is just symbolizing the abbreviation for the atom in the chemical formula. So in this example here, we have carbon, and it has a mass number of 12, and it has 6 protons. So we know that if it's a neutral atom, if it has 6 protons, it also has 6 electrons. And since this number is 12 right here, 12 minus 6 means there are also 6 neutrons. And so we will use this notation a lot when we do radioactivity equations, and also when we talk about just different isotope variants. So here's some practice. So if we look at this first one here, we see that we have a hydrogen and a 1. And that 1 is the atomic number. So we can say already, we know exactly how many protons it has. It has 1. And then we also know how many electrons the neutral atom has because it's the same as the number of protons, 1. And then for neutrons, we have to look at the atomic mass number, or the mass number, which is 2. And we see we only have 1 proton, so there must be 1 neutron as well. Oxygen 18 has 8 protons, 8 electrons, and then it has to have 10 neutrons because the mass of this particle is 18. Fluorine here has, again, 9 and 9, and then because this is 19, 19 minus 9 would be 10. And then carbon 13, 6 protons, 6 electrons, 7 neutrons. So most elements exist as mixtures of isotopes. And some elements, one isotope is way more abundant than others. Other isotopes or other elements have more of a mixture. So if we look at carbon, for example, almost all of it is carbon 12. There's a little bit of carbon 13 and there's trace amounts of 14. But you can see from the average atomic mass of carbon that it's mostly carbon 12. And for hydrogen, it's mostly the hydrogen 1. And then for oxygen, it's mostly oxygen 16. Note that the isotope symbol here, these are whole numbers. These whole numbers represent the number of protons and neutrons that are in a single atom. This over here represents the atomic mass or the average atomic mass that we would get when we average these things together. And so we look at, for example, our carbon, and we see 12. 12.011 comes from the weighted average of these two. Oxygen, we've got 16, 17, 18. And then we look at this and we see this is our average atomic mass. So this is the atomic mass that we would read on the periodic table. So we can practice this. Say we have an element and it exists as 2 different isotopes, so we can predict and then calculate the atomic mass. So we look here and we see this is 84.91 and 86.91 and the relative abundance. So 72%, 84.91, and 27.8, 86.91. So if I had to guess I would say that the atomic mass is probably between 85 and 86. And that's because we know that it's mostly this with a little bit of this, so it's going to raise the atomic mass a little bit, so it'll be greater than 84.91, which is pretty close to 85. So it's probably greater than 85, but not quite 86. So now we could actually calculate what our atomic mass for the element is. And to do that, we have to take 84.91 and we have to multiply that by the abundance, so 0.722, which is the same as 72.2 divided by 100, or 72.2%. And then we add 86.91 times 0.278. And when we add all this together, we get our average atomic mass of this element. And this works out to 85.47, which is right between 85 and 86. So you'll want to just remember that when we write in isotope notation, that we use a whole number to indicate the number of protons plus neutrons, and we use a whole number to indicate the number of protons, and that on the periodic table, we're more likely to see these, and these are weighted, these are the isotope masses that are more finely calculated with the percent abundance, and that to get the average atomic mass that you would see on the periodic table, you would need to do a weighted average.